Welcome. We have today Kenny Kubala from Focal. He's the co-founder and CTO of the company and has a strong background in digital imaging and optical engineering. Has successfully gone through the full product life cycle from concept to mass production with multiple technologies. He has over 20 publications, 7 issued patents, and 29 pending patents in different areas. He has graduated from the University of Arizona. He got his bachelor's degree there in optical engineering, and in this house he got his master and PhD in electrical engineering with a strong emphasis in optics.
Yeah, so don't ask me any electrical engineering questions. You might have a problem. So sorry, Kelvin. All right. Okay, so I'll start first by just a really super brief introduction of the company, since you guys probably haven't heard of us. We're about a year old, started last summer. There were four people that founded the company. Alan Barron, who has a background in optical sensing, myself, Rob Bates, who's our optical designer, and I promised Dad I'd mention that he won the International Optical Design Competition, so we're pretty excited about that. And if you lobby hard enough, maybe he'll come and do a talk here. But he's a really, really competent lens designer, very good at non-conventional lens design as well. Then Huck Wach, who graduated from University of Colorado as well, he was in Tom Cathy's group and did a lot of image signal processing. What we bring to the table is we have a lot of experience from the mobile imaging industry as well as others doing non-conventional types of optics, and our types of things that we work on are lens design, system design, signal processing, and then software. So those are really the areas that Focal works in. When we're doing things outside of these, doing development outside of these, we'll typically use consultants and subcontractors. So what are we going to talk about today? Really want to go through computational imaging. So what is computational imaging? Just a quick definition. Go through and talk about the general imaging system degrees of freedom. There's a lot of them, and they enable a lot of unique properties in imaging systems. Go through some examples. I think I have 7 or 8 examples of different types of computational imaging systems that use these degrees of freedom in special ways to create unique imaging properties. And then I'll talk a little bit more about extended depth of field approaches. And this talk was originally put together for the International Optical Design Conference, and there were a lot of people that had questions about extended depth of field. You'll notice, I'll show you this in a little bit, but there are, if you do a search, you'll find 9 or 10 different technologies for extended depth of field. Some of them are the exact same thing, and so I wanted to go through and talk a little bit about how do you compare these methods, which ones work better for which applications, and that sort of thing. And then really talk about trends in imaging systems and what we think is coming up next. So the definition I have is pretty simple. It's just for computational imaging, just a system that uses computation in the image forming process, and I'll have lots of examples of that. You may have also heard of computational photography. That's the term that came out of the computer vision community, and it's really a lot of times these are used interchangeably, the two terms. So first we'll talk a little bit about the degrees of freedom, and we'll just go through the 5 different aspects of it: the object, lens, sensor, ISP, which sometimes will interact with the network cloud, and the display, which will also sometimes interact with the networking cloud. And I'll give you some examples of that in a second. So the general characteristics of an object are its time varying 3-dimensional volume with varying absorption, transmission, and reflection. So that when you describe it that way, it really encompasses every object that you could imagine. There's illumination can either be self-generated. Examples of that are thermal or fluorescence. If you're imaging in the long wave IR, you're detecting the heat that's coming off of you. Or fluorescence is another good example. Or it could be a function of the object's illumination, such as what you have in here. You're getting a reflection of the spectrum from these lights. The reason this is a degree of freedom is you can use illumination as a variable, and you can I think I saw some Cairo guys. So this is an example of something that they're doing, is they're using illumination to try to better understand an object. And so that's why we consider this to be a degree of freedom in this example. And that can change as a function of intensity, space, time, spectrum, and polarization. And you can use all of those in different ways to better understand the object. The lens, the most general definition of a lens is it's really an angularly selective volume which allows the measurement of an electromagnetic field from distinct points on the object. And the reason I describe it this way is that that encompasses pinhole cameras and so-called lensless imagers and all sorts of imaging types of lenses in the general definition of a lens. And it's really a combination of reflective, refractive, absorptive material that can change as a function of time. So like a zoom lens, for example, will change as time, or adaptive optics can change with time. The sensor can be a single element, an array, or a volume of photosensitive regions. And there's, I'll show you an example of a single detector system. An array or volume would be, or array would be a typical CCD, and so like what Fovion's doing could be considered a volume where you're detecting colors with depth. Photosensitive regions, again, can have different sensitivities to color or spectra, polarization, so on and so forth. And you can read these out differently. You can have global shutters or rolling shutters that allow you probably saw a talk a few weeks ago on this, but allow you to take data out at the time that you want it. And so that's another degree of freedom on the sensor. Signal processing takes this temporally or spatially multiplexed data and either tries to make a really pretty picture or to accomplish a task. So pretty picture is obvious. Accomplish a task maybe when you're trying to read a barcode and it tells you, that's a water bottle or whatever it happens to be. In many cases, we're trying to enhance information beyond what a human can observe, and there are lots of examples of this in signal processing. I'll show you one of those in a second. And you're obviously bound by your available processing. And this is a good example where the network can be your signal processing. So there are applications on your phone where you take a picture of a business card. It sends that image to a server that then runs OCR on it and sends you back a contact. So that's a good example where you're using the network or cloud to actually do your signal processing. Then display really has two potential functions too. One is to basically display images for visual observation, so that's sort of the pretty picture one, or really trying to send actionable information, and these are the task-based types of imaging systems, where an example of that may be a pedestrian detection algorithm which tells you, or a camera that tells you that your car is on a crash course with a person, for example, and it's not going to give you a picture of the person, it's going to give you some sort of warning to tell you to beware. These also use the network. An example would be when you take a picture and it uploads it onto Flickr or Facebook or wherever it happens to take it, where your display is actually a PC that's remote from the camera. So we're now going to talk about how do you use all of these degrees of freedom that I just discussed and to make really special and interesting types of systems. That'll be our next section here. The first and most, one that you guys I'm sure have all seen is high dynamic range. So this is a example where you can take a short exposure and a long exposure, and you can basically tone map this high dynamic information to your display and see information that you couldn't see in either of these individually. The example is here you've saturated the information from the window, so it's essentially lost, and this stuff back here would have really low SNR if you tried to gain it up. So you've synthesized an image that's better than what you could observe from either of these individual photos. And that's a good computational imaging problem. You're taking two pictures, you're using some algorithms to create the final image, which may be better than what you could observe from a single snapshot. Another one here of an interesting one that uses some of these degrees of freedom is a motion magnification problem. And I should state, a lot of this work is not 5 focal, so I'm giving you a survey. So this was actually done by Ramesh Raskar at MIT. And And so I don't want you to think that this is our research, but this is to give you a broad overview of some of the things that you can do with these computational degrees of freedom. This is some work done at MIT, motion magnification. And what you can see here is, in this case, what they've done is actually amplified the motion of this beam that this person is swinging on. And this is something you obviously wouldn't observe in the video. And I'll show you a quick video here of an example that they have where, so we've got a guy pushing on the bookcase. You can't see a whole lot of motion there. You see a little bit. And the motion magnification will allow you to really amplify that. And you see it beyond what you'd normally observe. Another one of an image of a baby. And then you can see the motion magnified version of that. So I want to give you some nightmares. So that really doesn't happen. But the thing that they're exploring on the scientific side is looking at eardrums and things like that, where you really want to see the dynamics, and that amplification is really interesting in those cases. I think this one is a cool one that uses the network degree of freedom. This is was published in SIGGRAPH in 2007. It's taking an original picture here. This is what somebody took, and they cropped out this building because they didn't want it to be there. And what the algorithm will then do is search on the network. It'll look through millions of photos, and it'll try to find ones with characteristics like this original one. What it then does is it picks those, and it essentially maps it into that space where we cropped out this building, or where this building was cropped out. And you can see the final output. So this isn't a picture you could actually take, but it's more aesthetically pleasing than the original one. So a cool example where you've used the network in an interesting way to take data and fill a hole in an image. And I'm sure there's some scientific thing you could do with this, but I don't know what that is. This is, I think, a really interesting example that came out of Rice. This was a single pixel camera, and it's using compressive sampling. So give me a second to describe this because it's a little bit complicated. So here they're just shining light on an object. It's this R. They then image that onto a DMD, which is, you guys familiar with DMDs, I assume. So just little micro mirrors that you can switch on and off. They're in a lot of electronics these days. From the DMD, that's re-imaged just onto a single photodiode. So you can imagine now if you take this DMD and you just turn on the first pixel and then turn it off, and then the second pixel, you're essentially doing a raster scan of your object. So it's the simplest way of thinking, how would you create an image with a single pixel? But what these guys are actually doing is they're putting up a random pattern that they're changing frame to frame. So they'll put up a random pattern and then another random pattern and another random pattern. And what they're doing with that is essentially randomly sampling the power spectrum. When you take enough samples, you can use that to reconstruct or estimate what that object was. Here's an example of a 256 by 256 image that was created by 1,300 samples. So that's 2% of what you would do if you just had a grayscale image that would calculate that same R, or that would image that same R. Here's an example with 5%. And I think this is really interesting. I think the challenge is people instantly try to map it into, taking a picture of, the mountains or something that has a lot of texture and a lot of detail. You'll see even in the R, there's a lot of rough edges and a lot of artifacts which are due to missing information in that power spectrum that you're basically guessing what it is. So it's interesting from the perspective that you're able to do this with such little resources, but there's definitely an image quality hit in doing this. And it's not compressive like JPEG, because JPEG knows all of the spatial frequencies you want, or all the characteristics that you want, because it had seen the image and then it compresses. This is basically like randomly picking JPEG coefficients instead of picking the ones with the highest value. So there's a little bit of a trade-off there. But the other cool thing about this, I should state, is in cases where your sensor is extremely important, this is an interesting way of going about doing it, is you have a relatively cheap DMD, some relatively cheap, rest of the system's relatively cheap, and then you have your one expensive sensor. So I think they're trying to apply this to shortwave IR now, where your shortwave arrays are really, really expensive, and you could potentially have some cost benefit here. Coded aperture photography is another interesting one, and this is where, this came out of Ramesh Raskar's group as well, or Ramesh, I'm saying his name wrong. this is an example where, as you guys know, if you take a picture and something's moving really quickly, it gets really blurred. You can deconvolve that blur, but the problem is you'll have a lot of nulls in your transfer function, which is why you get these bands of ringing. So you have lots of artifacts if you just take and this was true with the Hubble too, when they tried to just use deconvolution to fix the Hubble problem back however long ago that was, 15 years ago. They had similar issues due to nulls in the transfer function. As you're seeing here, you got banding and artifacts that weren't present on the object. So what they've done here is they code the aperture, code the exposure, so it's not on the whole time. You'll have it on for a millisecond and then off and then on for 10 milliseconds and then off, and it'll basically go and use a temporal code that then gives you a blur that you can actually deconvolve. By doing this, you're filling in those nulls in the transfer function, and that's why the deconvolution works better here. If you look closely, you still have some image quality hit because you're relative to a full exposure if it was stationary, because you're not on the whole exposure, you're turning it off and on, so there is some light loss, and you see some of that in noise and that sort of thing in the black areas, for example, in this picture. Another one that you probably heard about is the light field photography, which is it's the planoptic camera, and I think not necessarily the first, but a good example of that was the Lavoie's work back in 2005. So he created a camera that was basically took a main lens objective, and this again uses some interesting degrees of freedom that I'll talk about here. Uses the main objective and then uses a micro lens array in front of the sensor. And so intuitively, what's this doing? It's re-imaging this pupil, and you're getting little images of the pupil on your sensor rather than the full image that you would normally see. So what you can do with this now is that your normal conjugate is, if you're just trying to image that conjugate here, you can just integrate all of the pixels behind each micro lens, and you'll have a lower resolution version of the camera that's now focused at this conjugate. If you want to focus or image something or focus the system after. So I should step back. The whole premise of this is you're capturing this 4D light field, and you're able to refocus the system later. So I would take a picture of this room. I could focus on you in the front row just by changing the reconstruction method, or I could focus on the back row, all with the same data set. So this is kind of interesting because it captures a large depth of field and allows you to synthetically focus after capture. And the way it's doing that, I jumped ahead, is in this case you're integrating all of the pixels behind the micro lens. In this case you're actually resampling this effective ray, that effective ray, and that effective ray to synthesize the focus that's pushed out beyond the conjugate that is shown here. So it's an interesting problem in that you're capturing different information, and you're using a relatively simple resampling algorithm to refocus the image after capture. So this is kind of cool for the point and shoot application. You could take your picture, you have all the data you need to go and synthesize whatever focus you want. You can always do things like fix the color with auto white balance or with white balance algorithms and that sort of thing. So it's going one step further towards that, being able to really take any picture and find a good picture within that set of data. The trade-off of this, I should state all these have trade-offs. The trade-off in this is that you're in this first example that they did, it was a 4,000 by 4,000 array, and the final image is 292 by 292. So there's a resolution trade-off in using this type of technique. Another really interesting one is called Tombow, and this is an effort to make an extremely thin camera. So to take a big bulky objective and shrink it down to something that's really compact and thin. And what they did here is they took a lens array and put it on top of essentially spacers on top of the photo detector array. And so what you image is this intermediate image. It's a bunch of images of this cat that are at low resolution. And if you're familiar with super resolution, it's trying to use super resolution techniques to understand the very small parallax you get between these images and to use those to your advantage. So it's trying to combine the very small shifts you would see to create this reconstructed image over here. So this is the sub-image, and theoretically in their model you could reconstruct this, although I don't think they used any noise or anything like that in that reconstruction. The next slide shows a little bit of the limitations and the challenges with this, as is true with general super resolution. So sub-image here, and this is the reconstructed image. And as you see here, there's a lot of artifacts, a lot of banding due to nulls in the pixel MTF, and it's not all that sharp, and that's also due to the poor SNR and the artifacts that come in as you try to reconstruct this sort of system. And I want to describe really quickly why do you have these limitations, and what I'm showing here is the MTF. As you know, the pixel MTF is just the Fourier transform of the pixel, so you're seeing sinc functions here. The first one is a sinc function with 100% fill factor, and that's my Nyquist frequency, so it's twice Nyquist. So if you're just trying to super resolve, a factor of 2, well, theoretically you can before you hit that first null. One thing you can do if you wanted to super resolve further is you can just decrease your fill factor. The difficulty with this is you're also reducing the number of photons that hit your photodetector. So you're reducing your SNR by taking this path. And there have been a lot of papers on a thing called diversity, where they're trying to slightly change the magnification of these sub-images, slightly rotate them to fill in those nulls in the pixel MTF. And that you can imagine would follow this red envelope in a perfect case. But the trade-off here that I'm describing is you'll still have a big SNR hit out at your high spatial frequencies, and it's my belief that this is why practically you'll see good examples of 2x super resolution from video, for example, with unknown shifts. If you have known shifts, I've seen some good examples of close to 3, but I've yet to see anything that really pushes this sort of limit, and it's my belief that these are the issues, right? They're fighting the pixel MTF and the poor SNR that you inherently get with that sort of system. But again, the value of this is these are really, really thin imagers. So if that's your goal and you can sacrifice image quality, this is potentially a way that you can go about doing that. So now we'll talk a little bit about extended depth of field, and then this will lead into the next section of the presentation. The extended depth of field technology really modifies the lens degrees of freedom. It uses the lens degrees of freedom in that you're changing the surface of the optic near the aperture stop. It uses the detector that the detector will sense that, or obviously detect the image, and you're using signal processing afterwards. So let me describe real quickly what's happening. In a traditional system, if you're in best focus, it's marked here by this red dotted line. And this red dotted line is without any perturbation to the imaging system. It's showing the MTF is high out to Nyquist frequency, and out here I have that at 100 cycles per millimeter. Again, good MTF. As I defocus, I get the second red dotted line, which shows really poor MTF. What these extended depth of field technologies do is they change the phase in the optic to give you this green line, and that's actually 2 curves there. So you're changing the phase to basically bring those curves together, and then you can use the same deconvolution kernel to amplify those up to this solid blue line. And that obviously is of much interest because you can become invariant to things like focus errors, field curvature, chromatic aberrations. You can make faster systems, one with higher fields of view. And we'll describe the trade-offs of this in the presentation, but that's the basic premise of this extended depth of field technology. It gets a little confusing because if you look at the literature, you'll find all of these names describing this type of technique. Wavefront coding really was the one that made it popular, and Ed Dowski's here. He was one of the, him and Tom Cathy came up with the wavefront coding technology, and we'll talk about that a little bit more. But you'll have a lot of other people that kind of litter the literature with a bunch of other stuff that kind of makes it confusing, but we'll compare a lot of these techniques here in the next few slides. So we'll dig a little deeper into extended depth of field approaches. And the first thing I wanted to do is describe how is this different than design for manufacturability. Design for manufacturability does something very similar. It takes your nominal design, which here are the 2 blue curves, and it allows you during design to sacrifice that nominal performance for better yield, essentially, better as-built performance. So it's allowing you to reduce your nominal MTF to give you better overall as-built MTF when you build the system. So very similar to what we just described with, or what I just described with wavefront coding. This DFM example shows that you can slightly reduce your nominal and greatly reduce your as-built MTF. So that's why this is very common in lens design. The primary difference is the EDOF techniques, they compromise MTF also, but they also directly consider the signal processing. So they don't just deplete the MTF, they consider how well is that matched to how I'm going to reconstruct this image. That's the primary difference between those two. So now going into the methods that I'll talk about, there's the cubic phase, which was created by Dowski and Cathy here at CU. And that's x to the third, y to the third type function. And again, when I talk about these phase functions, this is, you'd modify the surface near the pupil to make your wavefront look like this rather than something that was purely quadratic. So that's basically how you want to deviate your wavefront to give you this, this extended depth of field characteristic. We'll also compare that to rotationally symmetric systems, and what I'm showing here is not really what Nick George did is a log A sphere, and I'm not showing you a log A sphere, I'm showing you something that's optimized and better than a log A sphere, but this is a general class of rotationally symmetric systems that I'll look at. A technique called focus sweep, and the way the focus sweep creates a extended depth of field is it actually changes the focus during the exposure. So what it's going to do is you're imaging something, and I'm actually going to sweep something like an autofocus algorithm through conjugate during that exposure. So you can imagine during one instance of that exposure, there'll be a point in that volume which is in focus. So I'm going to capture an image, although it's going to be integrated with all these other out-of-focus images. At some point I'm going to capture a part that's in focus, and that's sort of how that maintains its high spatial frequency content. Then uses the same type of deconvolution to reconstruct the image and boost the MTF. The coded aperture approach, there are a bunch of these, but I just took the one by Levin from 2007. It's what it looks like. And the theory there was that this can also extend your depth of field. Levin also did a paper last year on segmented aperture, and the idea here was, why don't I just take a bunch of perfect lenses and cut them up and use these so that each little segment of the aperture focuses to a different conjugate, and then I theoretically can do something like this and capture, part of the image will be in focus because that segment of the aperture was tuned to that conjugate. This turns out it doesn't work very well when you consider a real physical model instead of just a geometric model, which is what they did in this paper. But I'll describe that in more detail shortly. Last one I'll compare is the spectral sweep, and the basic idea here is you can do something similar to what Hausler did here, but instead of changing, having quadratic phase that changes with time, you're going to do that with spectrum. And this is the same as axial chromatic aberration. So we're creating a quadratic phase that's going to change as a function of wavelength. So, for example, blue would focus really good at the table, and the red would focus really good at the far wall, and green would focus really well in between. By doing that, I can then make whichever channel is in best focus the Y channel or the spatial channel, and use the other channels to essentially color that, and those form the U and V channels. So these are the 6 models that we'll talk about, or I'll talk about. And the other key thing I should talk about the spectral sweep is I used a linear dispersion model on this. So as you guys know, with a typical glass, your dispersion is not linear. It's far from it, actually. But to make these comparisons as close as possible, I used a linear dispersion model for that one. So when you're looking at a normal image, all you really care about is the modulation transfer function at best focus. For these extended depth of field techniques, you actually really care about how that changes as a function of focus. So what does my MTF look like at the table, and what does it look like at the back wall? So the logical representation to our framework to describe these then is to just think of as an MTF stack where I've got MTFs here from different positions in Z. And from that I can always extract an MTF at any conjugate or any physical position in object space. I can also take a YZ slice which gives me a through focus MTF in this dimension or a one-dimensional MTF in this dimension, which I think is a good representation of looking at how things change as a function of focal position. And what this would tell me is, oh, right in here I've got a really good MTF, but as I move away it decreases, and that's what obviously happens with defocus. Or I can take a line from this plot and it's the typical through focus MTF curve that you'd have from an optical CAD program like ZMax or whatever it is that you're using. So the challenge with the previous representation is that it's extremely slow to calculate. Calculating MTFs as a function of conjugate is a slow method. So I'm going to talk through a way of calculating that quickly and then talk about the other advantages that you have of this method, which is it'll end up going to a 4D ambiguity function. So the 2D ambiguity function was described, has been described a lot in the literature. Dowski and Cathy use this a lot in defining the first cubic phase functions and deriving that. And what it does is it calculates a ambiguity function, which I'll describe what that has in there in a second, based on a 1D pupil function. So what you see here is basically the multiplication of the pupil with its shifted conjugate and complex conjugate, and then you're taking the Fourier transform of that. So for any spatial frequency, you can create a column in this by just shifting the 1D pupil, doing the multiplication, and then taking the 1D FFT of that. And what that gives you here is this is actually the through focus MTF plot that you're calculating with each of those shifts. So it's a really fast way of creating that through focus MTF rather than having to take a bunch of MTFs and sampling points on it. And the other interesting thing with that is as I take slices of this as a function of theta, it gives me a 1D MTF. So I can get through focus MTF and a 1D MTF from this really simple representation, a really simple equation. So what's interesting with this is the 2D ambiguity function really has the same information as the YZ slice that I showed you on the MTF stack. It can give you a through focus MTF and a 1D MTF in any position, except this was calculated in a much simpler way than the way that the MTF stack is calculated. So the challenge with the 2D function is it's using a 1D pupil, so you can extend this to a four-dimensional function. So we have our two frequency variables, two spatial variables, and it's the same math. So we're describing a pupil that's multiplied by a shifted the complex conjugate of itself, and taking a 2D Fourier transform will give you one of these 2D ambiguity functions. And I'm going to show you why that 4D function or the fourth dimension is interesting in a second. But in practice, the Y1 and Y2 spatial variables are coupled because you have a physical sensor. So that's basically saying that as I move my physical sensor, those two are going to add the same amount of quadratic phase. You can't pull apart X and Y with a physical sensor. That just describes the calculation of that. And what I'm going to show you now is a representation of this 4D ambiguity function, and this is going to lead into how you measure the efficiency of these different methods. So what we have here is the normalized spatial frequencies of the system. So this would be DC, and this would be half of the optical cutoff. And that's in both dimensions, in the X dimension and the Y dimension. Over here I just have a 2D MTF, so this is DC. This goes to high frequencies in the sagittal direction and high frequencies in the tangential direction. So the middle of each of these ambiguity functions represents a single point on that 2D MTF. So if I took the center of each of these 2D ambiguity functions, I would just take the point underneath that white dot, and it would be the same point that you'd have on a 2D MTF. as I go through focus, you'll notice that the modulation moves away from the physical point that the detector is detecting. And you see that in the MTF, the values are dropping, and you see that in the ambiguity function as the modulation moves away from the point that you're sampling. And I have some more examples of that here. So we have a lot of nulls in our MTF, and you can see that the detectable modulation is far away from that region that you're detecting with your system. So I'll go through in the negative direction. And what that just formed is basically what's been coined the focal manifold. So if I was trying to create an extended depth of field system that worked over that plus or minus one wave of defocus, I'd want all of my modulation to fall onto these white lines. And this defines my ideal ambiguity function would look something like this figure. I would have all my modulation, again, on the white lines. And if that's the case, I would be perfectly mapping, or most efficiently mapping my information to a through focus space. And this is the representation I'm going to use to compare the different methods. You'll be able to visually see the efficiency of each method using this type of figure in just a second. But before that, what you really care about is SNR and not modulation. And the reason for caring more about the signal-to-noise ratio is that this is what you're physically going to detect. When you just look at modulation, it's easy to ignore shot noise or signal-dependent noise, which is always going to be there. So this allows the representation to include noise that you can avoid. And basically, this is coming out of a paper by Paulo Silveira. He was in Kelvin's group here at CU a few years back, and he derived this the spatial frequency dependent SNR for task-based imaging systems. And basically, what we have here is the spatial frequency dependent SNR is a function of the mean SNR, the power spectrum of the object, the MTF, and then here we have this is due to the band-limited nature of detection or of task-based imagers. So for example, in a barcode, if you have spatial frequency information that goes beyond what's represented in the object, it shouldn't help your SNR. It's not relevant in that case. So this is representing that. In our case, since we want to look at general imagers, the two object-specific terms, the R term and the S term, we'll leave out. So we're basically looking at a function that's the MTF squared. So in doing that now all the backgrounds behind us, these shows the different representations or different ambiguity functions of these 6 different approaches. So the cubic you can see, and this is in the sagittal direction. So we're looking at a X spatial frequency at the Green-Nyquist frequency of a 3 meg system that it's operating at f2.8. So that's just to give you a little background. But ideally we want to, again, map all modulation onto a line that's in the horizontal direction. And you see that the cubic does a great job of that. The circularly symmetric has a lot of modulation on the axis, but it also wastes some away from the axis. And I'll show you the impact of that in a second. Focus sweep does a great job of keeping modulation on the axis, but you'll notice that it's lower than the cubic. And the main reason for that is when you're, with the focus sweep, you're incoherently combining images with time. So an image at focus position A can't coherently interfere with an image at focus position B because they're separated in time. So there's no chance of having additional constructive interference, which can help to increase your modulation as it does in the cubic. Spectral sweep is the same way. Your red plane wave won't interfere and create useful information with your blue plane wave, for example. The segmented aperture kind of falls apart, and I'll show you why that is in a few slides. But the modulation is really inconsistent, as is true with the coded aperture. So both of these have some issues, and so those will be left out of the further analysis. So the easiest way, I think, to compare these techniques is to now take a 1D plot along that focal manifold and just say, well, how much modulation do we really have that'll be detectable? And on this plot, I've added two more curves. The high black one is the full aperture system, so no change to the phase. This is what you'd see in a typical camera. The dotted black line is a stop-down version that's extended the depth of field by a factor of 3. So its first null is at 0.1, and the other null is at a negative 0.1. So these are the two baselines for comparison. So as you saw from the previous plot, the cubic, which is this top red curve, does very well in the sagittal and tangential direction. Doesn't do as well on the diagonals, and I'll talk about that in a further figure. The rotationally symmetric does relatively well. That's the green line, and then the blue line represents both the focus sweep and spectral sweep. When you use a linear dispersion with the spectral sweep, they end up having the same response. So now the next question is why did the cubic change on its diagonals? And the main reason for that is you saw the phase function. It's non-rotationally symmetric, so that means the OTF is also going to be non-rotationally symmetric. And what happens in that case is it's designed to optimally map modulation on the sagittal and tangential axis, but off axis it doesn't do as well. So this is one of the trade-offs to consider when thinking about using a cubic type function. The segmented aperture fell apart. Basically, in the paper, they had results that look kind of like this over here, and they were assuming incoherent combinations. So they were assuming that it was just a geometrical analysis, and they were looking at how many rays hit regions, and they were summing those, and that was how the modulation or signal was calculated. And the problem with that is as people that have worked with segmented aperture telescopes, for example, is that if you take one of your segments out of phase, it doesn't just add a nice incoherent blur to your system. It actually will beat against the other plane waves that are creating your nice sharp PSF. So in that case, when you start considering the coherence of the different apertures, you get this funny beating, which really kills your through focus MTF and your 2D ambiguity function, which is shown here. So the other thing to consider is, although I think modulation in SNR is extremely important, the other thing when thinking about extended depth of field systems that needs to be considered is the PSF and signal processing. This first example shows the object and a reconstructed object when you're using a cubic where the filter or the deconvolution kernel was built away from this PSF. So this is kind of characteristic of cubics when you get far away from best focuses. You get these artifacts which look like shadows in your image. So for a pretty picture, this is a difficult thing to deal with, but for task-based imagers, you probably don't actually care. You can still create very effective systems with that sort of phase function. But these artifacts are something that has to be considered during the design phase. The other thing that has to be considered, or the other two things, are the size of your deconvolution kernel directly relates to the control that you have in your spatial frequency amplification. So this is true in Photoshop, this is true with computational imaging, this is true with all deconvolution kernels, is that if you have say a 5x5 kernel, as in this example, you're going to lose 1 degree of freedom just to make the gain be the same. So if you don't want to change the brightness, you have to use 1 degree of freedom to make that constant. You'll lose 2 of them due to symmetry in your kernel, and then the other 2 are your inflection points that you can control in your MTF. So the challenge with this is you need to make sure that when you reduce your MTF with an extended depth of field technology, you need to make sure it's matched with how you can boost it in frequency space, or else you'll end up with hazy type images and other artifacts that are undesirable. The other thing to consider is the extent of the kernel. That's another very important thing. Is obviously your reconstruction, your signal processing has to have the same extent of the kernel, or you're going to have artifacts as well. So going quickly through the pros and cons of the different approaches. As I mentioned, cubic's good in 2 dimensions, horizontal and vertical. The cons is it has to be keyed with your sensor typically, and it also has to be keyed with your signal processing, meaning that if you take a convolution kernel and then rotate the phase plate, you won't reconstruct it correctly. Circularly symmetric is nice in that it's easy to manufacture, has good out of focus characteristics, and has symmetric artifacts which typically aren't as distracting for photographic applications. But it's less efficient than a cubic along the horizontal or the sagittal and tangential directions. Spectral sweep is very similar to the circularly symmetric, but has the additional con that you need to be able to do signal-dependent processing, meaning that if you're reconstructing something close, you're going to use more of the blue channel, and something far, you're going to use more of the red channel. Focus sweep is dynamic, which is nice. So if you have an autofocus actuator, you can sweep. That has to be fast, obviously. You can sweep during exposure and have either extended depth of field or not. You can either turn it on or off. So that's an interesting characteristic of that one. Segmented aperture has the value that you can also create a depth map. So it's kind of interesting from that point of view, although the example I showed wasn't great. You could probably optimize that to make it better. And depth map is something that you could potentially be interested in having. The coded aperture is, I think it's really, its only advantage is it's really easy to implement. You can go at home and create one and put it in your camera and you're good to go. But it doesn't have very good characteristics outside of that. So now talking quickly through the design considerations. So when you're designing extended depth of field systems, it's quite different than traditional design, that you're just using wavefront error or spot-based metrics. And these are inefficient away from best focus, and the main reason for that is your wavefront error can either have a wavefront that gives you a good MTF or a bad MTF with the same wavefront error. So not all wavefront errors are created equal. So that makes that a pretty bad metric for optimizing through focus types of systems. So really you need to optimize on MTF, and the key thing here is that when you optimize on MTF, for any of you that have done design, is it's really works very poorly with the ampli squares optimizers. So and the reason for that is you end up hitting these lots of local minima when you get into a side lobe of a through focus MTF, for example, and it's very hard to get past that. So I'll give you an example and some of the tricks that you can use to get past that. And the design example is a simple one. It's just meant to have pretty picture at infinity and read barcode close. And this is sort of interest to a lot of markets, specifically the cell phone market. It'd be nice to be able to do both of those with the same fixed focus camera without having autofocus, because it's technically cheaper. The merit function you do for that is you would have a different figure of merit for infinity than close. And here I'm just describing this as the MTF thresholds. You'd need a couple of those out to Green Nyquist. And what you're optimizing there is MTF value, shape, and then the spatial extent of the PSF. So those are the things that you'd put in your merit function. For the barcode, you really care about having modulation that's high enough to be able for the barcode algorithm to work. And here we've chosen a value of 0.3. And also the barcode's critical frequency. So the barcode spatial frequencies obviously become smaller as it moves closer to the camera. So in using these really simple figures of merit, you can create something that looks like this, an infinity MTF and a 15 centimeter MTF that meets those specifications. And this can be done either in an iterative sense where you're going to manually push through the optimization, or it can be done with using a different optimizer than Dampli squares. But this was an example that was created in ZMAX, and I think Rob did this when we were driving up to the conference. I think he spent about 30 minutes on it. So this is something that you can do really quickly with an existing design code. So I want to talk really briefly about what's next. So what we think is an interesting direction is that, we talked a little bit about the ISP and the display being leveraging the network, and it's a logical extension to think that that'll extend to the objects and the lens and the sensor. And you may say, well, what does that really mean? And in my mind, what that means is if you have information about for example, the time of day your camera can set or the weather, the camera can set the right white balance for those conditions. Or if you're trying to do a task, you can precondition your sensor to look closely at certain areas and object space, for example. And I think trying to exploit more information in the front-end system is a really interesting trend that we think is going to have a lot of traction going forward. So as I mentioned, just systems with heavier reliance on the networking cloud, having them be massively adaptive and more information efficient. Example of that may be if I'm in the dark, I only use the long wave spectrum. If it's bright daylight, I use visible or something simple like that. But having the ability to adapt, I think, is really important. And then really the future is intelligence in the imaging system. And we're seeing a lot of this already in automotive systems that are going to use they're going to detect body position and adjust the airbag to deploy better for the person sitting there. Pedestrian detection systems, things like that. So I think the addition of mating novel optics with very advanced signal processing is certainly going to be a big trend going forward, especially in the commercial world. So the basic conclusions are lots of degrees of freedom that you can use, and I showed you some examples of how you use those in special ways. And some of those have really interesting benefits using the degrees of freedom in special ways. And the other point is this isn't inaccessible to anybody. So a lot of people have pitched in the past that you need these really complicated design methodologies to create these systems, and we personally would disagree with that. We think you can do a lot of these things with very simple tools, which makes it accessible to everyone in the room that has access to design tools and that sort of thing. So that is the end. Any questions?
Going back to design of cubic face or all the face parts within the beauty function, do you think there exists potential for other types of geometries for those wavefront coding type elements other than cubics, or do you think cubics really make the best for you?
Oh, I think there are. I think there's huge opportunity for that, and I think I don't think many people have the fundamental understanding of how to use the 4D ambiguity function, and I think that's one of the things that Ed Dowski and Tom Cathy exploited here at CU, is they created that by understanding the math. And this math isn't new. It goes back to the 60s, and the optical version of it was in a paper by Brenner, this 4D in 1982, I think. But the understanding of that is still limited. So I think as people start to understand the use of this as a tool, I do think there's opportunities for better designs, certainly. Kelvin.
Is there an interaction between the spectral sweep method and the kind of Bayer filter or photon detector? Is it better or worse? What if you had more color channels?
So are you talking about interaction if we are detecting in depth with our sensor as well when you're talking about foveon, or? Well, just the fact that or would it be better if we had more color channels? Yeah, certainly. So if you had, what limits that is fundamentally you're still, so if you take your large band and I have a limited depth of field and now I break it into 2 color bands, I can theoretically double that depth of field because I still have interband axial chromatic that's going to deplete my MTF. Does that make sense? So as I make that finer and finer and finer, the more I can extend that. So if you had a something with a I guess as it goes to 0, your depth of field theoretically goes to infinity. But yeah, so I think the more bands, the limitation of having the intra-band or say green, red, or blue axial chromatic deplete your MTF becomes less. Does that make sense? Did I answer your question? Okay.
What about the spatial effects of Bayer filters interacting with that technique?
The spatial effects. So I think you still have the typical aliasing that you would have. It doesn't help that, and I don't believe that it makes that worse. Or if you went to a super hyperspectral system where you had sparser sampling in a green channel, for example, it'd obviously impact your resolution. But I don't think there are. To the best of my knowledge, I don't think there are any other funny effects other than the typical aliasing that you would have. Ed, what do you think? Do you agree with that? Yeah, yeah. Right, all right, all right. Yeah, Raphael. Absolutely, the goal for the design of all those was a 3x. I probably didn't say that very clearly, but to go from, for this example, minus 100 microns to plus 100 microns in image space was the design. So they all have the same design goal. That's correct. That's a really good question. You'll find designing these that they snap really well into a certain depth of field, and then you'll struggle and they'll snap into another depth of field. So I think there are natural depth of fields that certain phase functions do better at. So that's an excellent question. That would be an interesting study to look at SNR as a function of depth of field and see if it modulates in any funny way with the different functions. And I would guess that it does, although I have no proof. But I guess that it does just based on experience. Any other questions?
If there are no more questions, thanks.
Thank you.